Welcome back, guys. Day 9 problems. Start with number 1. The brilliant red colors seen in fireworks are due to the emissions of light with wavelengths around 650 nanometers when strontium salts are heated. Calculate, there's my verb, calculate the frequency and energy of red light with the wavelength 650. So, my formulas. Come to the top here. C equals lambda nu. E equals h nu. And combining the h nu. Combining these two formulas, E equals h c over lambda, right? So those are my two formulas and then the combination of energy and wavelength. So, let's see here. I have C equals lambda equals nu equals E equals h equals. And so I know C and H, 3.00 times 10 to the 8th meters per second. 6.626 times 10 to negative 34 joules times seconds. I have 650 nanometers. I do not know my frequency, and I do not know my energy. Well, I think I should find the frequency first, right? So, C is lambda nu. That means nu equals C over lambda, correct? So nu is going to equal 3.00 times 10 to the 8 meters per second divided by 650 nanometers. Well, nano means times 10 to the minus 9 meters. It's very important to get our units the same, right? So my frequency is what? So how do I put this in the calculator? That's another one. Okay, so got the calculator out. Now, 3.00 is the same thing as 3 in your calculator. Does that make sense? So 3 or 3.00. I use the second button and this TI-84 plus and this EE, which is the comma. Second, EE 8. All right? 8. Divide 650, second, comma, negative 9. So now it has number and number, and I get 4.62 times 10 to the 14th. Now I only have 2 sig figs, so it's 4.6 times 10 to the 14th. 4.6 times 10 to the 14th, 1 over seconds, or hertz, same thing. And so now I got my frequency. Now it's time for the energy. E equals h nu. So E equals h. 6.626 times 10 to negative 34 joules times seconds. Multiplied by 4.6 times 10 to the 14th, 1 over seconds. So our energy happens to be, now, I'm going to cheat. I'm just going to do times, and it takes this answer times 6.626 times 10 to the negative 34. 3.1 times 10 to the negative 19th joules. Which seems small, doesn't it? Negative 19th. Except, that kind of makes sense, doesn't it? When somebody turns the light on, you don't get knocked over by all the energy coming at you, right? Right? It's not like I'm turning on the lights and you have to like hold on to the desk or your bed or your chair, and that's not what happens, right? Okay, now calculator. If I'm going to type in Planck's constant a lot, I can go 6.626 times 10 to the negative 34, and I can use this store button down here for the variable x. And every time I hit x now, it's that variable. Right? So I could have done 0.62 times 10 to the 14th times x, and I get my answer again. A little bit different because I use less numbers. But there you go. So you can do that as well. All right, so going to number 2. Maybe. Maybe not. Oh, no, way too far. Number 2, an FM radio station broadcasts at 99.5 megahertz. Calculate the wavelength. All right, so that's C equals lambda nu, right? Or lambda equals C over nu. So my wavelength will equal C. What's C? I got 3 sig figs, so 3.00 times 10 to the 8th meters per second. Megahertz here. So I have 99.5. Mega is times 10 to the 6, 1 over seconds. And so my wavelength, 3 times 10 to the 8th divided by 99.5 times 10 to the 6th. I get 3.02 meters. Meters. There we go. Number 3. What's the energy of a blue photon? Well, I'm going to use E equals hc over lambda, right? E equals h, 6.626 times 10 to negative 34 joules times seconds. C, 3.00 times 10 to the 8 meters per second. Wavelength, 400 nanometers times 10 to the minus 9 meters. So that my energy is what? Well, let's go to X, 6.626 times 10 to the negative 34 times 3 times 10 to the 8, divide 400 times 10, negative 9. And I get I actually get 5 times 10 to the negative 19th, because that's only 1 sig fig. And there's number 3. Number 4. All right, now if you look at number 4, I have how many sig figs here? So this photon has energy here, right? And that's 1, 2, 3, 4, 5 sig figs. I'm looking for the wavelength here. What is the wavelength? Okay, so E equals hc over lambda, or E times wavelength is hc, or lambda equals hc over E, right? We can do that. So my wavelength will equal hc over E. H is 6.626. Ooh. I have 1, 2, 3, 4, 5 sig figs. So I'm going to have to go back to my sheet and get more numbers for Planck's constant, which is 0.7. I like to do that. Times 10 to negative 34 joules times seconds. Light, I'm going to use 2.99792 times 10 to the 8 meters per second. And then I'm going to use 2.8397 times 10 to the negative 19 joules. So now I have 5 sig figs there. I have 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. So I have an extra sig fig in each of my numbers, my constants, which gives me peace of mind knowing that my measurement of energy is the limiting factor, not my constants. All right. So what is my wavelength? So I can't use my X anymore. I have to use 6.62607 times 10 to the negative 34 times 2.99792 times 10 to the 8 divide 2.8 397 times 10 to the negative 19th. And I get 6.9953, I believe. Right, I got how many sig figs? I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 6.9953. .9953 times 10 to the negative 7th meters, which happens to be 699.53 times 10 to the negative 9th meters, which is 699.53. Wow, writing today. Nanometers, which we can measure. I can measure that in this room with some of my instruments. All right, available to me. They're not mine. They're the school's. All right, so that's not unreasonable. That's not an unreasonable number of sig figs. Okay, number 5. Almost done. What's the energy of an X-ray photon with a frequency of 1 times 10 to the 20th? So, what's the energy? E of, right, h nu equals h nu. So E equals 6.626 times 10 to the negative 34 joules times seconds. Why did I just use that number? Well, 1 sig fig, 4 sig figs. 1 sig fig is fine. Right, this is good. Times 1 times 10 to the 20th, 1 over seconds. So my energy would be 6.626 times 10 to the negative 14 joules, or 7 times 10 to the negative 14 joules, right? Because I only have 1 sig fig. Number 6. What's the energy of a UV photon with the wavelength 320 nanometers? Well, I'm going to use E equals h nu over lambda, right? Not h nu, hc over lambda, right? E equals hc, E equals, well, before we get there, C equals lambda nu. So C over lambda is nu, and plug that in to E equals hc over lambda. 6.626 times 10 to the negative 34 joules times second. There's Planck's constant. Speed of light, 3.00 times 10 to the 8th meters per second. 320 times 10 to the negative 9th meters. All right, so my energy will be, all right, h, which I have x still, times 3 times 10 to the 8th. Oh, didn't do that right. 3 second EE, 8, yep. Divide by 320 times 10 to the negative 9th. 6.2 times 10 to the negative 19th joules. There we go. Number 7. Now, number 7 is the exact same thing. I'm just changing the wavelength, right? You notice that? I'm going from 320 to 250. Okay, so E equals hc over lambda again. So that's 6.626 10 to the negative 34 joules times seconds. 3.00 times 10 to the 8th meters per second, all over 250 times 10 to the negative 9 meters. Now, the main reason we're doing this one is if I hit second, hit enter, the same thing comes up. And I can just go to, oh, too far, make this 250, done. And so when we get longer, that's a really convenient thing. And so that's basically 7.95 or 8.0 times 10 to the negative 19 joules. So hopefully that explains the C equals lambda nu, E equals H nu, and gives you ideas how to work with the problems, how to work with the calculator to make sure you get the right exponent, because that's very important. All right, guys, thanks for watching. We'll see you next time.